homogeneous version of the wave equation with no forcing function. All right. Um, no damping terms, just very vanilla version of the wave equation. And so, the methods that we'll develop to study this in this chapter are specific to this equation. They're not as general as eigenfunction methods. But if we happen to encounter this type of problem, these methods can be a little bit more revealing than eigenfunction expansions. And this equation is fairly common. And so the argument is that it's worth having this sort of very specialized tool in your toolbox for the situations where you do encounter this type of problem. And the solution can be shown you can write it in this form. Known as D'Alembert's solution. All right. That if you don't worry about the boundary conditions for now, and we'll see why that's okay in a minute, we're just concerned with the equation itself. You can write the solution to that PDE in this form. And we showed that this is something that moves to the right, and this is something that moves to the left. And it doesn't matter what f is. Any function of f acting on x minus ct is a solution to the wave equation. And any function g acting on the sum x plus ct is also a solution. And because the wave equation is linear, you can add the two together in any combination. So anything moving to the left plus anything moving to the right with speed c is a solution. All right. And you can verify this by inserting this form into the equation itself. All right. So what is UTT? That's going to be two time derivatives. Because of the chain rule, every time we take a time derivative of f, we're going to have an f prime, but we're going to pull out a factor of minus c. All right. So we're going to get a minus c quantity squared f double prime of x minus ct. And then the same is going to be true here for g. When we take two time derivatives, we're going to pull out positive c quantity squared g prime prime of x plus ct. And of course, negative c quantity squared is just c squared. And then uxx, if we say what is the right-hand side, c squared uxx, that's going to be c squared times the x derivative of this sum. Well, what is the x derivative of this sum? The x derivative of this sum, when I take two derivatives with respect to x, those are just going to be primes. F prime prime x minus ct plus g prime prime x plus ct. And you can see right there that utt does in fact equal c squared uxx, right, for this sum. So that's definitely a solution to the wave equation. If we talk about trying to satisfy these initial conditions, that's where things got kind of hurried last lecture. We can simply insert this form, f of x minus ct plus g of x plus ct, into the initial conditions. All right, so what do we get? What is u of x comma 0? We do this just like anytime we satisfy initial conditions. We write down the left-hand side, u of x comma 0. What is that going to be? Well, if t is 0, then ct is 0. So we're just going to have f of x plus g of x plus 0. And that is going to have to be I0 of x. And then u sub t of x0. Well, when we take a time derivative of f, we're going to pull out a minus c. So minus c f prime. but then we evaluate that at t equals 0. So that's going to be evaluated just at x. And then we have to take the time derivative of g, which is going to pull out a factor of positive c, g prime. And then we evaluate that at t equals 0. So it's just going to be an x. And that has to equal I1 of x. All right. Now, we have two equations for two unknowns. And we can take this second equation, we can integrate both sides of it and divide it by negative c, right? So we'll get f of x minus g of x equals negative 1 over c integral from 0 to x of I1 of, and then this needs to be some different letter, all right? And we could say x bar, dx bar. All right. So now we have very clearly two equations for the two unknowns, f and g, right? So we're not given f and g, we're given the two initial conditions, the initial condition on the value of u and the initial condition on the time derivative of u. If we were to try and solve this equation, our goal would be to determine what function f and what function of g to use in D'Alembert's solution to satisfy those initial conditions. What is the shape of the thing moving to the left? What is the shape of the thing moving to the right? So that's what we're doing here. We now have two equations for two unknowns. We can solve them in sort of standard ways. You know, when you have them written in this form, one of them is f plus g, one of them is f minus g. A standard trick is to like add the two equations together and then subtract the two equations. So if we add them together and divide by 2, we get f of x equals 1/2. You know, the g's will cancel, and then we'll divide the sum of these two things. I0 of x minus 1 over c, integral from 0 to x, I1 of x bar dx bar. Should be a bar there. And then if we subtract the two equations and divide by 2, we get g of x equals 1/2 I0 of x bar plus 1 over c integral from 0 to x of I1 x bar dx.
I'm sorry, but what's x bar again?
X bar is just some dummy integration variable. All right. This is basically a way of writing like the indefinite integral. Is you put the variable in the upper bound of integration, and then you have a dummy variable on the inside. So as x changes, this whole thing, is some function of x, right? Because when you integrate in x bar, the x bar gets integrated out, and then you apply the bounds at 0 and x. And so the result of this process right here is some function of x, right? It's kind of an indirect way of writing the indefinite or the antiderivative of I1, basically. It's worth highlighting and noting that what is this? This is just the antiderivative of I1 of x. Sorry, you have these tools that let you do interesting things with things that you've written down, and then like OCD things kick in. So here we have this way to find f and g, right? And what we showed last time is that f is a function that moves to the right, g moves to the left, and if all you have is an initial displacement and no initial velocity, then these two terms disappear. Okay, don't do that because this is just hypothetical. Okay, if, in fact, let me not do that. Okay, let me Go back to pen. If I1 of x equals 0, then u of x and t equals f of x minus ct plus g of x plus ct equals what? There's a common factor of a half. And then what is f? F is I naught, the function 1/2 I naught. And its argument is now this x gets replaced with x minus ct, right? If this is f of x, then f of x minus ct is going to be 1/2 I naught of x minus ct. And then what is g? G is going to be 1/2 I naught x plus ct. And so what this says is that in the case where you have just an initial displacement, no initial velocity, then the solution is very simple. You take the initial condition, you multiply it by half, and then you send 1/2 to the left and 1/2 to the right. And that's it. Right? And that's what we saw in our marked up notes that I can return to. Here was this example. All right. We took an example where we have a wave speed of just 1, and the initial condition is just a square rectangular bump that goes from -1 to 1 up here. All right. Then 1/2 of that is something that is 1/2 unit high instead of 1 unit high. And so we should expect our solution to be a bump 1/2 unit high, 2 units wide moving to the left, and a bump 1/2 unit high, 2 units wide moving to the right. Okay. And here we tried to draw that. There's our initial condition. In red, that's what we would have gotten if we were doing an eigenfunction solution, because we've got discontinuous functions, which is one reason why these sort of techniques are worth exploring, is that you can completely sidestep that problem because we don't have eigenfunctions anymore. So we take our initial condition, we sort of split it vertically. I'll come back to that. I have to be a little bit careful when I say things like split it, because really what we're doing is multiplying it by a half. All right. We're not actually slicing it horizontally. We're multiplying it by a half. And this thing multiplied by a half, we have 2 of them. One of them moves to the left, one of them moves to the right. And that's what our solution looks like in time. All right. For a while, they still overlap. And in the region where they overlap, they still add up to 1. All right. But as they move away from each other, eventually they no longer overlap, and we no longer have any parts of the solution that add up to 1. They just add up to 1/2, and they're moving in each direction. So when I say we have to be careful about splitting things, and when I use language like split it in half or cut it in half, suppose you have an example. In fact, let me go back to my other page. I'll publish both of these. Oh, shoot, you guys can't see this, can you? You can only see.
I see the page with U of X at T.
Yeah, that's right. Sorry, I changed windows on my desktop, and I thought you could see them as well, but just a second. You saw me just scroll a little bit, right?
Yes.
Okay. So let me do another example. It's different than the one I did. All right. Suppose our initial condition so again, wave speed of 1, I0 of x equals, and I'm just going to draw it. All right. So say instead, and this is what we saw in the video that we did with eigenfunction expansions. Okay, say it is a triangle now. All right, and I1 of x equals 0. what does it mean, to cut that in half? And when I use language like that, people can sometimes get confused. So at t equals 0, our solution is just the initial condition, right? Like this. What we really have is the superposition of two triangles that are half this height. Okay, we don't actually cut it in half, like this, and send this trapezoid to the left and send this smaller triangle to the right, right? That's not what we're doing. We also don't cut it in half like here and send the left side to the left and the right hand side to the left. And so that's the kinds of things that the language cut in half can make people sometimes think that we're trying to do. That is not true at all. Instead, what we have is two triangles that are half the size that are on top of each other, adding up to a taller triangle that goes to 1. Okay, and so now if we let the blue one go to the right and the green one the green one go to the right and the blue one go to the left, then we'll get interesting behavior, say at t equals 1/2. Okay, let's draw the two triangles. They'll each have moved a half a unit. So this one will now have gone to -1.5. And it will stretch all the way to +1/2. All right. And this green one will stretch from -0.5 all the way to 1.5. Okay, and so what does the sum of these look like? Well, that's a little bit more complicated. From -0.5 from -3/2 to -1/2, the sum of them is simply the blue. And from 1/2 to 3/2, the sum of them is simply this blue line with slope -0.5 and +0.5. But in between, looks like we're gonna have a straight line. All right, so that's what our solution will look like at t equals 1/2. And then by t equals 1, they have moved, so they are no longer overlapping. Okay, and we'll just have half height triangle, half height triangle. Right, this is the blue, and this is the green. All right, so here's another example. So that's pretty straightforward, right? What is less straightforward is what happens if there is, instead of an initial displacement, there is an initial velocity. All right, so let me now go back to my printed notes. Okay, so now we have the initial displacement is 0, but the initial velocity has that little square rectangle shape, right? So this is the same shape, but now it's in I1 instead of I0. Okay, so if we go back to our result here, basically, what this says is that f of x is negative, and in this example, c is 1, negative the integral from 0 to x of I, right? So it's negative antiderivative of I1. And g is the positive antiderivative of I1. Okay? Or another way you could say this, which is how I've set it up in the notes, is that f prime, the derivative of f, is negative I1, and g prime, the derivative of g, is positive I1. So that's how I've set it up in this this image here. So it's a bit harder to visualize. I start with f prime and g prime, and I apologize. I have made oh shoot, I've labeled them wrong. I've labeled them opposite each other as well. Okay, I'll fix that. This is the thing moving to the left. The thing moving to the left, we have been calling g. Okay, not f. G. And the thing moving to the right, we've been calling f. And the other mistake I've made is that f prime is, like I just said, negative negative I. So let me color over this with white so that it's not there to confuse us. Okay, there. Now my notes are consistent with everything I have just said. F prime is negative I, 1/2 negative I. G prime is 1/2 I. So we need to find f and g. And to do that, we take the integral from 0 to x of f and g. So to find the integral of f prime, we integrate from 0 to x. What this says is that the slope is negative. If I'm integrating from 0 to x, then when I am at 0, f is 0, right? If f is defined as the integral from 0 to x of I1, then f of 0 is 0, and g of 0 is 0. And then as I integrate, say to the right, I'm getting more and more negative. As I integrate to the left, I'm getting more and more positive, all right, until I reach 1 or negative 1. If I'm integrating to the right, I get more and more negative until I reach 1, at which point I have reached a value of negative 1/2. And from that point onward, f prime is 0, and my integral no longer increases. Similarly, as I'm integrating to the left, I get more and more positive until I reach negative 1, at which point I've reached a value of 1/2, and I no longer increase. And the same is true for g, except that g prime is positive where f prime is negative. And so the slope is 1/2 instead of negative 1/2, and you get this sort of mirror image. Okay, now how does this play out if this is our f and this is our g? Well, this shape moves to the right and this shape moves to the left. At t equals 0, these two things cancel. And I'll draw them on top of each other again. So green is the thing moving to the right. We've got our 1 and our negative 1. Right? Green is the thing moving to the right. And it looks like this. Right? And then blue is moving to the left. And it looks like this. Okay? And at t equals 0, these cancel. They add up to 0. Consistent with the initial condition, right? The initial condition is 0. But what happens after that? Well, this green thing moves to the right. And by t equals 1, it has shifted 1 unit to the right. So it now looks like this. And the blue thing now looks like wait, I'm getting ahead of myself here. The blue thing now looks like this. Okay, and if we add those two things together, again, they feel like I've made a mistake here. In my drawing, there's 0 far away from the origin. They add up to 1 at x equals 0. And then where I feel like I've made a mistake is that I think I've drawn this black thing wrong. I think it's not as wide as it needs to be. Let's do t equals 2 just to check. So now my green edge will have moved here out to x equals 1. It will decrease to here, go here. My blue thing will have moved one more unit to the left. So it will look like this. Yep, I did make a mistake. I didn't realize that last time when I did this. So let me just fix that. All right, and instead, it looks like this. This still looks the same. We have this unit from this flat plateau at the top, and then it gradually decreases like this. So same idea, I just had it not quite wide enough.
Wouldn't that triangle in the top picture be the same height as it used to be? Since they're adding up.
Yes. So it would be like this. Good catch. Good. Okay. So very good. Okay, I think we all are on the same page now. So the picture was qualitatively correct, quantitatively incorrect. So this is interesting, right? When you have an initial displacement, a bump, the bump kind of splits in half and moves away from the center, and the center is left as it was initially, right? The bumps move to the left and right, and then in the end, the center is 0 again. But when you have an initial velocity, you have this interesting phenomenon that you do have these things moving to the left and right, but when they've moved far away from the center, the position of the center is now permanently displaced. All right, it never goes back to 0. So that's interesting, and it's just a different different phenomenon. Displacement yields a different phenomenon than an initial displacement yields a different phenomenon than an initial velocity. So imagine again, my favorite, like this is an example of like a piano where you have a hammer that hits a string instead of a harp where you displace the string and then let it go, if you hit that string, it induces a slightly different type of wave phenomenon than if you displace and release. Now, some general commentary on the nature of D'Alembert's solution, right? You have this thing moving to the left, this thing moving to the right, no matter the initial conditions. And that sets up an interesting diagram that you can draw. All right, so here's another spatiotemporal diagram. We have here an x-axis and a t-axis. And suppose we have some event that happens at x naught t naught. It can be any value of x, any value of t. Or suppose we're just observing there. If something happens at x naught t naught to change the shape of the string, that information is going to travel to the right and to the left at speed c. All right. And if we have just a displacement, then that ultimately leaves no permanent change to the displacement of the string at x naught. But if we have an initial velocity imparted, it does result in a permanent change. And so this whole region between the left moving and the right moving waves is in principle influenced by what happens at x naught t naught. And that sets up what we call a range of influence. That at all future times within these boundaries, the value of the function in this range can be influenced by what happened at x naught t naught. It cannot be influenced. X naught t naught cannot influence points out here. If I'm an observer sitting at this point, I cannot detect what happened at x naught t naught because that information has not reached me yet. All right, that information will not reach me until some later time. Similarly, if I'm an observer at x naught t naught, information may have reached me from a variety of places contained within what we call the domain of dependence. The value of the function at this point x naught t naught can in principle depend on anything that happens in this triangular shaped domain of dependence, but it cannot depend on something that happens outside that domain of dependence, right? For exactly the same reason, the information will not have been traveling fast enough to reach this red dot by this time. That information will travel at the same speed and it will not be detectable by someone standing at x naught until some later time, t naught plus, plus something. And this principle, this feature of the wave equation, that it has a finite range of influence and a finite domain of dependence that grow as you stretch forward and backward in time, is something that you encounter in at least two contexts I can think of. One is if you've ever been to like a baseball game, you can detect this phenomenon where, like, if something loud happens far away that you can also see, you can tell that light and sound travel at different speeds because you can see it happen before you can hear it happen. Right? So, say you're an observer sitting far away, you see it effectively at the same time it happens. But imagine you were blind and you were just listening. You would, in fact, not hear something that happens far away until several seconds after it happened. Okay? Because you would be an observer here, say, and something happens over there. Well, there's going to be a time delay before you receive that information because sound only travels so fast. And similarly, if you yell something or if you produce a sound, right, you will only be heard by people within your range of influence after a certain amount of time. And if someone's farther away, it's going to take them longer to hear you. Now, a context in which this is even more prevalent is astronomy. All right. So, we live in a vast universe, and light seems pretty fast on the scale of Earth. Light can travel around the entire Earth, something like 7 times a second, which seems very fast. It's effectively instantaneous. Um, but once you're starting to talk about distances as vast as the distances in even just the solar system, really, but especially once you start talking about distances across the universe, light's actually not that fast, right? It takes like 8 minutes to get from the sun to Earth. It takes like an hour or multiple hours to get back and forth from Earth to like the Voyager probes that are reaching the edge of the solar system. And it takes many years to get even from our closest neighbor star to us. So when we see things happening out in the universe, we're here at, sorry, say we're here at like the present. All right. If we see something happening and it's very far away, then that information had to travel to us along this line, right? And if it's very far away, then that means it happened a long time ago. And what we're really seeing is something that happened way back in the past that is far away. And this is why astronomers who are trying to figure out what happened at the beginning of the universe need really big telescopes. All right. So it's possible to view back in time if you can view far enough away. And so we build these massive telescopes. We build telescopes that we can send into space so that they don't have to wrestle with things like disturbance and interference in the Earth's atmosphere, all so that we can look at things very, very, very far away. And the reason we're interested in looking at things very, 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 very far away is not because we'll ever go there. It's because it tells us about things that happened a very, very, very long time ago. All right. And understanding how we got where we are is potentially useful. And so that's why we have to look at things so far away. So, you hear things, like, for instance, maybe you read some articles about, I don't know, they pop up on my news feed, but I'm like interested in astronomy. So there's a star, that's sort of a famous star in the sky called, like, everybody calls it Betelgeuse. I think it's technically pronounced like Betelgeuse or something like this. I don't really know, but it's one of the brighter stars in the sky. It's in the constellation Orion. And does anybody know what happened to it over the last few months?
Did it finally pop?
You would have known. If that had happened, you'd have gone outside in the middle of the night and said, why is it still daytime? Okay, maybe maybe not everybody follows like astronomy news. It was getting dimmer. Like, it's one of the brightest stars in the sky, and it was sort of mysteriously getting dimmer over the course of several months. It got like it reached just a fraction of its typical brightness. And this is a star that we know is sort of at the end of its life. It's near the end of its lifespan. But in the time scale of stars, near the end of its life doesn't mean a whole lot. It's not very precise on human time scales. So the star is basically could explode anytime between now and like a million years from now, which is pretty soon over the lifetime of a star. And so, it's getting dimmer. It's a star that tends to get brighter and dimmer over time, but it seemed to be getting especially dim this time. And so people were like, oh, maybe it's exploded, maybe it's about to explode. And all of the articles mention the fact, they at least referred to this sort of time delay, that because of light only travels so fast, it could have exploded already and we wouldn't know it, because that information would take a solid, 600 years to reach us, because that star is 600 light years away. So everything that we see happening there is what really happened 600 years ago. And the farther away something is, the farther back in time what we're observing actually happened. This is not a good point in the class to start a new topic. So we'll just end there. Kind of a light lecture today. Does anybody have any questions so far on anything, even just like astronomy? See, one thing I like about this is like none of these properties of the wave equation, they all seem pretty obvious when you explain them in this way, but none of them are obvious from the eigenfunction solution, right? When you do the transform and you get the infinite sum, it's not at all obvious that information travels at a fixed speed and you have a range of influence and a domain of dependence, and it's great for like calculating a solution, but this approach that we're talking about right now, I think definitely provides a lot more intuition about how the wave equation behaves. I will post this on Canvas. With the numbers, in this unit, a lot of the examples will have more to do with shapes. So like the 3 examples where we drew pictures are sort of typical examples of homework problems from what we've done so far. I will say leaning more towards the theoretical. So like next lecture will be figuring out what happens at a boundary condition. And we're going to do some math, but there won't really be any numbers in that. Instead, when we do the math is going to tell us something that we can understand geometrically. Okay. And in fact, you've already seen it in that we're going to show why when a traveling wave hits a Dirichlet boundary condition, it bounces back upside down, right? So that's the result that we've sort of already seen, but we're going to prove that that happens all the time. And then from that point forward, I'll be able to give you more difficult homework, which is like, okay, draw the evolution of this solution. Not only what happens to the bump, but then also tell me what happens after these bumps bounce off their respective boundaries, right? So you'll be drawing more pictures than calculating stuff. Yes, Juliana. So that extra time derivative, that first time derivative, is not part of the spatial operator, right? So it stays on the left-hand side, and you take its transform, just like you take the transform of the second time derivative. And so what you get is a second order ODE with both second derivative terms and first derivative terms in the final steps of the problem. Yep. And what you learned back in ODEs is that when you have that first derivative term in there, it's interpreted as what we call a damping term. It gradually decreases the amplitude of the oscillations over time. And so that's why, when you hit a key on a piano or you pluck a string on a harp or a guitar, it gradually gets quieter over time, right? Because there's air resistance that is slowing the string down over time. And then there are like internal resistances as the string expands and contracts. Some of its kinetic energy gets turned into heat. And so over time, musical instruments, fade away. Their pitch volume decays. And that's kind of what that problem is getting at.
Did you play the viola in high school?
Yes, I did.
Oh boy, I played the tuba.
Ah, very different instruments, but
Yes, it is.
Yep. Yeah, I played all through high school, and I even played. I started college actually as a double major in math and music performance, and I played in the Meadows Symphony for a year.
Oh, that's
before
cool.
I kind of burned out. Bass guitar, yeah, not so different. At least it's strings. We string players have to stick together. In problem 2, how should we deal with piecewise initial condition? All you do is split the transform integral into 2 parts. And that's it. You're taking the transform in space of the PDE as a whole, and that's fine. There's no discontinuities or piecewise definitions there. And then you also take the transform of both initial conditions. And if those are defined in a piecewise manner, then the numerator of that transform integral is broken into several pieces, and that's it. The denominator stays in one piece, and at the end you get, some number that depends on n, just like before. Any other homework questions? This is a great time for homework questions. If not, you guys are free to go. Have a nice weekend. Find a
Have a
way
nice
to
weekend.
make it feel different than the rest of the week, which is challenging these days. But good luck on that, and we'll see you on Monday.